Yeah, so this is the rough outline of my talk is as follows. So whenever I say inequality, you can also think of optimization. It will show up in my talk why you can always think of inequalities as optimization. Okay, so the outline of my talk is going to be as follows. I'm going to first talk about what is called a family of inequalities called the Brascamp-Lieb inequalities. Brascamp-Lieb inequalities. I'll basically explain where they show up as functional inequalities, and then try to establish a connection of these families of inequalities to information theory. I'll very quickly also talk about a completely different family of entropy inequalities, which are called entropy power inequalities. Entropy power inequalities. So these are call them EPIs, and this is the BLI. And I'll highlight what are the differences between the similarities and differences between these two families of inequalities. And lastly, when I'm done with these two, I'll talk about is there a bigger story. Essentially, the last section of this talk will be something about unifying these two families of inequalities. This last part is joint work with Chandra Nair, who is here, and Venkat, my advisor. Venkat Anantaram. So I'll talk about how to get a more general family of inequalities that combines both Brascamp-Lieb inequalities and entropy power inequalities. Okay. So yeah, so this last part is unifying ELI and EPI. All right. So please feel free to stop me if you have any questions. I'll take a break at maybe somewhere after 0.2 or 0.1, depending on how long it takes. Okay. All right. So let's start. So Brascamp-Lieb inequality. So before I start with this family of Brascamp-Lieb inequalities, you might be familiar with other families of inequalities that show up all the time. So one is before Young's inequality, even simpler, something like Holder's inequality. Okay. So Holder's inequality says that you have a bunch of functions, and you're looking at integral of product of, so you have these integrable positive functions. So let's say fj of x to the pj, and let's say this is less equal product of integral of fj. So I'm ignoring all the dx's, but there are also dx's sitting everywhere to the pj when the sum of pj's is 1. Okay, so that's an example. This is Holder's inequality stated maybe somewhat differently than what you're used to. Usually, you might have seen it with norms, p norms, and so on. But this is an equivalent representation of Holder's inequality. Another inequality is what is called, let's say, the Loomis-Whitney inequality. Loomis-Whitney. Yes, non-negative functions and integrable functions. Yeah. Okay, so everywhere in this whole talk there will be non-negative functions. Okay. So Loomis-Whitney inequality, one way to think about it is from a geometric perspective. So I'll quickly give what the geometric idea is before writing the inequality. The geometric idea is, suppose you have some set sitting in Rn. So let's draw a picture in R3. So this is some set K, which is a subset of Rn. Let's say bounded and compact set. And you take this set and you take its shadows on the x, y, y, z, and the zx planes. So you take a shadow here, and some shadow here and behind. The Loomis-Whitney inequality is an inequality that tries to tell you something about the size of this set based on its 3 shadows. Okay, so intuitively it says that if all the shadows are small, then the object can't be very big because its shadows in all 3 directions are small. Okay, the functional form of Loomis-Whitney is what I write. So the functional form reduces to this shadow form if you choose your functions to be indicator functions in the appropriate dimensions. Okay, so what we are now going to say is, suppose there are 3 functions there is f1 here, f2 here, and f3 here. So this is in the xy plane, yz plane, and the zx plane. So start with 3 functions. So in general, you can start with f1, f2, dot 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 fn. These are, say again, non-negative functions on Rn minus 1, Rn minus 1 to, let's say, R plus. So the Loomis-Whitney inequality is going to say that you define, it's going to look similar. So you look at the integral of the product of fi of, so I'm going to write this as p sub I of x, where p sub I is just a projection. So it takes an n-dimensional vector x1, x2, xn, x1, x2, xn, and maps it to x1, x2, dot 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 dot, xi minus 1, xi plus 1, dot 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 xn. Okay, so it basically just projects it onto ei perpendicular, the subspace. Okay. So if you have a point x, y, z here, when you project it here, it becomes xy. So you got rid of the z and so on. Okay. So you consider the product of these functions fi. So pi of x is now in the correct dimension, Rn minus 1, and you raise it to the power 1 over n minus 1, and you get this inequality that this is less equal product of these integral of fi to the 1 over n minus 1. 1 to n. So here the integral is over Rn, and here all these integrals are over Rn minus 1. So if you were to choose fi to be indicator functions of these shadows, then you would get that on the right hand side you would get the product of the volumes of these shadows raised to the power 1 over n minus 1, and on the left hand side you would get the largest possible volume of this set, right? Because if a set is going to have, if these are the shadows, then the biggest possible set which could have these shadows is a point where the indicator function in all these 3 directions is 1, because it has to correspond, that shadow has to correspond to some point there. All right, so that's the Loomis-Whitney inequality, and I'll.
One question is suggested that you can take projection over arbitrary states, not just these.
Yes. Yes, yeah. So I'll come to that in a bit. Yeah. Right. That's holders, Loomis-Whitney. Actually, leave this right here. Okay, and the last inequality is a Young's inequality for convolution. So again, you probably might have seen it in a different format, Young's inequality. But here the way I'm going to write it is, it's equivalent to the classical format of Young's inequality. So it says consider 3 functions now, so f1, f2, f3, which are, say, functions from some r to the d to r plus, and consider 3 numbers p1, p2, p3 such that sum of the pi's is 2. Okay. So Young's inequality for convolution states that you look at f1 of x to the p1, f2 of x minus y to the p2, and f3 of y to the p3. So this is the integral of the product. It happens to be less than or equal to product of the integral. So integral of f1 to the p1, 2, 3. But this time something strange happens. So you have this inequality, but there is this there is a correction constant here. So the constant is not 1. You get a c times the rest of the thing, where the c is given by 1 minus p1 to the 1 minus p1 times 1 minus p2 to 1 minus p2 divided by p1 to the p1, p2 to the p2, p3 to the p3, and whole to the d by 2. So it's some constant that does not depend on the functions, it just depends on the parameters of the inequality, p1, p2, p3, and d. Right? Okay, So that's all. These are just 3 examples of inequalities that I want to write on the board to motivate Brascamp-Lieb inequalities. Okay. So if you look at these 3 inequalities, you can kind of see what are the common elements in the 3 of them. So all 3 of them look of the following form: integral of a product is less than product of an integral. So that's one thing that is common. Another thing is on the left hand side, you always have some kind of a linear transformation of x. So x is a point in Rn. In Holder's inequality, you basically were projecting it. So let's talk about Loomis-Whitney in that case. So in Loomis-Whitney, you have a point x in Rn, and you're projecting it into Rn minus 1 by some linear transformation. Similarly, in Young's inequality, if you were to think of your point as x, y, z, then the function x1 is taking a point x, y, z and mapping it to x1, which is a linear transformation. f2 is taking x, y, z and mapping it to x minus y, again a linear transformation. And f3 is taking x, y, z, mapping it to y, again a linear transformation. Okay, so the 2 common elements are on the left hand side, you always have integral of a product. On the right hand side, you always have product of an integral. And on the left hand side, you have some linear transformation showing up. Okay, so you could write all these inequalities in a common format as follows. So let's say you have this set Rn. So Rn is going to be this large vector whose linear transformation we are going to take. So for example, in this case, Rn would correspond to this xyz kind of a set. Right? So you have Rn, and you have a bunch of other smaller spaces. Let's say R to the n1, R to the n2, and say R to the nm. And you have linear maps going from Rn to these smaller spaces. Okay, so linear map is just a matrix. So we might as well just represent these maps by matrices of the appropriate sizes. Let's say these matrices are B1, B2, Bm. Okay, so now the left hand side of these families of inequalities can be written as you want to write integral of a product of functions. So these functions, we have m such functions. So let's say j going from 1 to m. So fj of bjx and this whole thing to some pj. Okay, and this integral is over Rn. So this the left hand side that I've written is clearly generalizing the left hand sides of all these 3 families of inequalities. And the right hand side, now you would just write as integral of fj of x dx, where the integral is over the correct dimension. So r to the nj, you take this to the pj, and product from j going from 1 to n. Okay, so that's the left hand side, that's the right hand side. To get an inequality, what you would like is left hand side is less than or equal to something times the right hand side. Not exactly the right hand side, because in the Young's inequality we did have a constant which was kind of correcting things. So what one would like is the left hand side is less than some c times the right hand side. Okay, so this is not yet an inequality. We haven't stated anything. We haven't said a result. We have just said that all these 3 families of inequalities are the same as can be written in this format. Good. So right now there are no constraints on the PJs. They're positive numbers, non-zero numbers, but that's it. Oops, sorry. It can be anything. So I mean, we haven't yet figured out what that constant is. It can be less than or greater than 1. Yeah. Okay. So this is the formulation that we would be interested in. So really, when you ask the question, well, does an inequality of this form hold? You really are trying to solve this optimization problem. So C you can think of as the worst possible constant. So C has to be this over that. No, that over this. Okay, so C is supremum of, let's see what I've written. So you want to have the worst possible the constant, which means C has to be less than or equal to something, which means, okay, I will try to write integral C. Integral FG. Okay, so you're basically trying to take the left hand side divided by the right hand side and say that so C has to be greater than or equal to whatever that is. So this is the supremum. Yeah. Okay. So if you want to say that such an inequality holds for all possible classes of functions that you could think of, or all possible functions that you could think of, you want to try and solve this optimization problem over all such functions f1, f2, fm. So I didn't mention what these fi's are. So there is a function f1 defined on Rn1, f2 defined on Rn2, and fm defined on Rnm. So f1, f2, fm are the things that are in your hand. You can select any function that you like. Select any function that you like, plug into this fraction, you'll get some value. Try to maximize that value over all possible values of these choices of these functions, and that's the optimization problem that we have at hand. So if this problem has like finite value of C, then you have an inequality in your hand. So you have an inequality which says left hand side is less than some constant times the right hand side, which is generalizing all these three families of inequalities. If C happens to be infinite, then you don't have any inequality. All you have is left hand side is less than infinity, which is always true. Okay. Sorry? B1 is just a matrix that is taking, linear transformation. So,
and then on the integral, the denominator is just on Rn, there is no, not depending on when you project.
So this denominator? Yeah, this is just the integral on Rn. Yeah. I mean, you could say that PJ are actually projection, BJ are projection matrices, but it doesn't change the nature of.
I don't understand the bound of the integral. There is the first one is over the whole space, and the second one.
Yes. So the first one, you're taking an x sitting in Rn. You're first then projecting it via b1, b2, bn to take these bj of x functions, and then you're applying f1 to b1 of x, f2 to b2 of x, and fm to bm of x, and you're multiplying all these fis to the pis. And the second one is now you forget this space, you only focus on this space. You take the integral of this f function on Rm or on the correct subspace. So just take the integral of fj of x over r to the nj. So this dx is now ranging over r to the nj. So you're right, like there is some scaling that the bj will do, which will get incorporated in the constant.
Okay, so this
Yeah.
is why it's not appearing.
That's why it's not, yeah, so we don't care about it, it'll just get absorbed in the constant, yeah. So this constant is, so this C is a function of all the BIs and the PIs, I going from 1 to M. So it'll get absorbed in the constant if your B is some scaled version of a projection. All right. Any other questions? Okay, so this is the optimization problem in hand, and this is a very hard problem if you look at it, because it's an infinite dimensional problem. You have to optimize over these M functions. So it doesn't seem clear how to solve it and whether this value is even going to be finite. Okay, so that's where Brascamp-Lieb's theorem comes into picture. So this was a result proved by Lieb. Okay, and he showed the following, that to find C, it is enough to consider functions centered Gaussian functions. So centered Gaussian functions. So what by that I mean that pick your function fj to be something like e to the minus of x transpose a x with some, so the scaling can just go into this picture where A is an Nj cross Nj positive definite weight. Yes. Yes, so Fi is a function from in its own space. So R to the Ni to R. So when you take Fi of Bi of x, the original x is in Rn, Bi of x maps it to R to the Ni, then you apply Fi to it. So this is Rn. When you apply Bi, you land up in R to the Ni, and then when you apply Fi to this, you land up in R. Yeah. Okay. Okay. So coming back to the theorem of Lieb. So this theorem says that it is enough to consider only centered Gaussian functions. What does that mean? Well, clearly if you only focus on functions which look like this, and you try to calculate the maximum possible value of C that you would get using functions like this, you would get some kind of a lower bound, because you are only considering a subset of functions. But this non-trivial theorem is saying that whatever maximum value you get using these functions is the same as that you would get if you were to use all possible functions. Okay, and why is this relevant? This is kind of important because the original optimization problem was this infinite dimensional problem over f1, f2, fm. But now, if you are told that it is enough to consider these kinds of functions, so I'll call this matrix AJ, then our optimization problem now reduces to the space of matrices A1, A2, ... AM, where A1, A2, AM are in the appropriate dimensions and they're positive definite. So suddenly you have gone from infinite dimensions to finite dimensions, and you can also write. So you can actually compute these integrals when you have Gaussian functions like of this form, and this function C happens to be of this form. So supremum over these A1, A2, AM of the appropriate form of something over something, and this something is product of determinant of AJ to the PJ divided by determinant of sum of PJ and then J. Okay, so it's some kind of a determinant maximize. The numerator is a product of determinants, and the denominator is a determinant of some sum of these AJs. Okay, so even this. So FGs, we plugged this particular. So we didn't actually plug this particular form. We plugged this particular form. So the scaling doesn't matter. You can always. So this is a pi. So the pi is there to make integrations easier. So we said that pick Fj to be that specific choice for some AJ. And clearly this class of Fj's that you're considering is much smaller than the set of all possible functions. Yes. Yeah. So Fj of x is equal to e to the minus pi x transpose Aj x. Yeah. 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 That's what I'll come to. Yes. Sorry, say again. Yeah, there is a reason. So that's what I'll come to. So looking at the functional form, I don't have much intuition for what this result is saying. Okay. So the functional form, I mean this particular form, it says that here is an optimization problem which is infinite dimensional, and you suddenly say that you don't need to consider everything, just consider Gaussian, and that's a theorem. That's about where my understanding was 3 years ago when I first read it. Like this is a theorem, this is true, but I didn't know what to do with it. Okay, so that's what I'll come to. Like for me, what helped was getting a different kind of an interpretation of this problem through a paper by Carlin and Cordero-Erosquin. So there was a paper in 2007, I think,
So
October.
you're saying that there is no initial proof, then any intuition?
I didn't get any intuition from the initial proof. Yeah, that's it. Maybe, I mean, if you're working in functional analysis,